used in the RMS prob. Here is usually said to be 0.999. So, and the epsilon, remember the epsilon we use to avoid dividing by 0, okay, is usually set by, 10 to the power negative 7, okay. Well, I mean, yeah, they are hyperparameter, but we normally do not need to tune those hyperparameters. And because it's a adaptive optimizer, okay, it means that we even do not need to tune the learning rate, okay, because learning rate will be tuned automatically if it's adaptive optimizer. So it's going to be just like this, okay. Keras star optimizers, Adam, if you want to use it, okay. Just specify learning rate, specify beta 1, beta 2. That's it. But I mean, normally you don't need to, change those values. You just need to provide the default value should work just fine, okay. So since Adam is an adaptive learning algorithm, so it requires less tuning of the learning rate hyperparameter, okay. So you can often use the default learning rate, okay, making EDA even easier to use than gradient descent. So a lot of people, okay, just use Adam directly, okay. So but of course there are some considerations I will talk about shortly, okay. And the other variant of Adam optimization is called Adam Max. ADA Max, okay. ADA Max, okay, basically, okay, replace the L2 norm by L infinite norm, okay. So what is L2 norm? L2 norm, remember, it's like the L2 norm is this thing. I'm sorry. Here. This one is L2 norm, okay, and we sort of kind of estimate the L2 norm, and then we divide, okay, this by L2 norm. So we want to replace this by the L infinite norm. So what is L infinite norm? Okay, L infinite, I mean, is if you have some components, L2 norm is that just square sum of those things, okay, and with square root, that's L2 norm. But L infinite just means, okay, if you have some component, you just use the maximal value out of those components. It's called L infinite. Okay, very simple, very simple. Okay, so here, okay, if you want to use L infinite norm, okay, we are going to replace, okay, this S to be max beta 2S and this one. Okay, so we are going to the second line is going to be maximal, the max value of this one or this one. This one. Okay, and then, okay, also, okay, the last line, it'll drop the line 4, okay, because now, okay, because we set it to be L max, okay, L infinite, so there's no, we don't have an issue of starting the S value too small because, because we are taking the bigger one of these two. And no matter which one we take, okay, it's not going to start from 0 anyway, okay. But the last line, I think that's it. Drop line 4 in the step 5. Okay, it scaled down the gradient update by a factor of S. So. So just don't use square root, just use S. Okay, and we don't need epsilon here anymore. Okay, so that's we call this eta max, okay? And the eta max actually, okay, most of the time, okay, I mean, Adam still perform better. So what is the advantage of eta max? The eta max, this change, okay, changing the L2 norm to L infinite norm, okay, should make eta max more stable than Adam. Okay, that's theoretically speaking. Okay, but as I said, okay, it depends on data set, and in general, Adam still perform better. Okay, so this is just one more optimizer you can try. Okay, if you experience a problem with Adam. Okay, so the third one in the Adam family is called Naden. Okay, so Naden is actually very simple. Okay, remember Adam is a combination of momentum and the RMS prop, right? So Naden, what's Naden? Naden is a combination of natural gradient, accelerated gradient, okay, and RMS prop. Okay, so it just replace the momentum with NAG. Okay, so we are trying to estimate at the next step. Okay, that's it. So this is like the only difference. But the Naden, okay, some people say like Naden generally outperform Adam, but sometimes outperformed by RMS prop. Okay, so active optimization methods such as RMS prop, Adam and Naden, okay, all these adaptive optimization are often great, okay, converging faster, okay, to a good solution. However, okay, there's a catch here, okay. There's a 2017 paper, okay, point out that this adaptive optimization method may lead to solutions that generalize poorly on some data sets. Okay, so it is not always the case that adaptive optimization is always better. I probably can say it's a lot of time they are better, but it's just in case, okay, when you are disappointed by your model's performance, okay, if you are using adaptive optimizer, okay, and the training, and the model you obtained, the performance is disappointed, then you should try using plain NAG, okay, or even momentum, because like your data set may just be allergic to adaptive gradients, because some data set may not be suitable for adaptive optimization. Okay, so also check out the latest research on optimization technique, because it is moving fast. This area actually is active research. So from time to time there are like new optimization techniques proposed. Okay, but basically, okay, if you know these few optimizers, to start with, I think you should be good. Okay. And also, okay, all these optimization techniques that I have talked about, okay, including momentum, including, or even include like the SGD, okay, and the momentum, and what else? NAG and ELA grade, the RMS prop, Adam, ELA max, Naden, okay. All these optimization techniques, okay, rely on first order partial derivatives. Okay, we call them Jacobian, okay, in mathematics, okay, the first partial order. Okay, the optimization literature also contain, algorithms based on second order partial derivatives. We call those second order partial derivatives, we call them Hessian. Okay, but we normally do not use those algorithms that is based on second order partial derivatives. Okay, why? Because in deep learning, we have a lot of parameters. Okay, each weight is considered a parameter. Okay, so if you are talking about like a order one, like a first order, then say if you have like a 1,000 like hyperparameters, I mean sorry, 1,000 like parameters, then yeah, I only need to calculate like 1,000 partial derivatives. But if you are talking, I mean the second order, then it's going to be something like this, right? Right? And this x1, x2 can be any parameter. So if you have like a 1,000, then it immediately becomes like a million, right? So you have too many this partial derivative to calculate. Okay, so a lot of time, okay, those partial derivatives, often don't even fit in the memory. Okay, because there are too many. Okay, when I say 1,000, I mean that's really like a very small number. Remember, like a small. Remember we use like the model summary to show like how many trainable parameter. Remember? Okay, we normally end up with like just a very small model. End up with like tens of thousands of parameters, right? So this second order, okay, is like the square of those numbers. Okay, so it's going to be very, very big. Okay, so unfortunately, okay, even though there are many amazing, algorithms, amazing like optimization algorithm based on second order partial derivatives, but because second order partial derivatives are too many to calculate, okay, for deep learning, so we normally don't use them. Okay. It's already. Let's take 10 minutes break. Okay. When we come back, we will continue discussion. Okay.